Hi, my name is Krutik Alapati, and this is my Lab 2 on lines of charge. The objective of this lab was to expand upon the goals from Lab 1 of learning how charges work, but introduce the concept of lines of charge rather than an analysis of just point charges. So why is this important? Well, modeling line charges as opposed to point charges is more accurate in the case of two pieces of tape interacting with each other. It is far more likely that the charge on the tape will be distributed along it rather than just being a point charge at the center of the tape. The results from the experiment were that the two tapes repelled each other and likely had a positive charge since the tape was attracted to the negatively charged pen. The charge on the tape was calculated to be 1.54 times 10 to the negative 8 coulombs, and the magnitude of the electric and gravitational forces was determined to be 2.93 times 10 to the negative 3 newtons. So here are the concepts and formulas that we'll be using. So to begin with, we're going to be using Newton's second law, since we're going to be analyzing the forces in a system. And since there's no net acceleration, we can set the forces net equal to the net force of 0 to determine the charge on the tapes. We'll be using Coulomb's law to determine the electric force, as we're going to be looking at the two charges interacting with each other, or in the case of lines of charge, many charges. And we'll also be looking at the force due to the electric field caused by these charges, which the formula is shown here as well. And we'll be looking at superposition and distribution of charge, since the net charge of an object can be determined by dividing the object into infinitely small pieces and summing the charges of those pieces. So for the experiment, the system was tape A and tape B, and the surroundings were the universe surrounding the tape. The tape started from a neutral charge, and the only initial force on the tape is gravity. So to create the U-tape, we stuck a piece of tape to the desk to create a base tape, and then I created a charge on the U-tape by sticking a second piece of tape to the first and ripping it off. And this process was repeated to create two charged tapes. So the assumptions for this week are that there is no air resistance on the tapes. Each piece of tape has the same charge, and I'm assuming the charge is evenly distributed along the pieces of tape. The expectation for the experiment was that the tape should be attracted to neutral objects. Since the tapes are expected to hold similar charges, they should repel each other, and if the tape is positively charged, it should be attracted to the negatively charged pen, and vice versa. It should be repelled by the negatively charged pen if it's negative. So the observations and conclusions were that the charged tapes repelled each other, the charged tape was attracted to neutral objects, as well as the negatively charged pen, and there was no acceleration on either tape after the initial repulsion, meaning that the charges are the same. Here are my calculations from week 1, showing that since the force electric is equal to the force of gravity, we can set them equal to each other since the net force is 0, and use the formulas shown in the Newton's second law formula and the Coulomb's law formula to calculate the charge, which was for this model, it was determined to be 1.54 times 10 to the negative 8 coulombs. And here you can see the rest of the calculations shown on this slide. Here you can see my GlowScript code. On the left side, we have some constants, the acceleration due to gravity and the universal constant, and the mass of the tape measured from week 1. I also included the charge of the tape from the point charge model from week 1, as well as the charge calculated from this model through trial and error, which was 3.5374 e negative 8 coulombs. Below that, you can see the function used to model the electric field. On the top right side, you can see the two lines of code used to model the top and bottom tape, and in this I included the separation, which was 0.027 meters, as well as the length, which is 0.25 meters. And what's also included is n equals 50, which is how many sections the code will break the tape model into, which is 50 sections in this case. And below that is the function, which adds the force electric in each of these 50 segments and sums them to get the net electric force. Below that, we have the model for the arrows of the force gravity and force electric. And below that, we have the print statements for the magnitudes of these forces. So here's the GlowScript model showing the code from the last slide, and you can see each of those red dots is a segment of the tape, and each of those green lines is the electric force from the bottom tape, and the model adds it all up, and you get the gravitational and electric force equal to 2.943 e negative 3. So the error in this is that the tape likely lost charge while being handled. There's human error in the measurement. The charges on the tape are likely different, and the charge is likely not equally distributed among the tape. Although it's more accurate than the point charge model, the line charge model is not as accurate as integrating infinitesimally small portions of the tape. When compared to the point charge model from last week, the line of charge model resulted in a larger calculation for the charge, which is 3.5374 e negative 8 coulombs versus 1.54 e negative 8 coulombs. And this is likely due to the charge existing distributed among the tape rather than a point charge at the center of the tape, making the line of charge model more accurate than the point charge model.